Unbalanced 3-wire Y configurations necessitate a wholly different approach. As I previously alluded, load elements in unbalanced 3-wire Y configurations might not even experience the same voltage magnitude, to say nothing of current magnitude, relative phase shift, and apparent, real, and reactive power, principally because any imbalanced current is left to circulate throughout this system, messing it up along the way. This tiger not only has teeth, it's wearing a bulletproof vest and night vision goggles. I found the easiest way to approach an unbalanced 3-wire Y configuration is to swing the superposition theorem over your head like a torch and simply charge at it, stomping your feet and yelling while doing so. This seemingly fearsome tiger spooks rather easily. Consider a 208 volt 60 Hz 3-phase AC source supplying power to an unbalanced 3-wire Y configuration. Let's use our previous unbalanced configuration, meant to simulate an industrial 3-phase AC motor that may have something wrong with winding 1, only it's being employed in a 3-wire system this time. Let's see how this system responds. Load impedance Z1 has a magnitude of 535 ohms at an angle of 51 degrees. This is the odd man out. Load impedance Z2 has a magnitude of 365 ohms at an angle of 28 degrees. And finally, load impedance Z3 has a magnitude of 365 ohms at an angle of 28 degrees. This is again the definition of an unbalanced load. Impedance Z1 has a different magnitude and angle than either Z2 or Z3. To apply the superposition theorem, we need to look inside our sources. Let's assume it's a Y configuration of three 120 volt 60 Hz AC sources offset by a relative 120 degrees, making it indirectly appear as if there was a 208 volt line-to-line differential, also offset by a relative 120 degrees. The only difference from our previous 4-wire Y arrangement is that the central node is no longer accessible and no relief path for imbalance current exists. Let's apply the superposition theorem from the top down. First L2, then L1, then L3, then a final summation accounting for not only magnitude and phase shift, but also polarity and direction. Using these final summated voltage and current figures, we can then solve for nonlinear properties like power. If you feel you're up to the challenge, by all means, pause the lecture and try this on your own. If you're tracking, you should have come up with the following values. To analyze this system from the perspective of only source L2, we remove sources L1 and L3 by substituting a short circuit or low impedance path. This modification has fundamentally changed the nature of our original circuit. It appears as if Z1, our odd impedance, is in parallel with Z3, a simplification I'm calling Z double prime. The parallel combination of Z1 and Z3 presents a combined impedance of 221.3 ohms at an angle of 37.3 degrees. Z2 and Z double prime appear to be perfectly in series with one another. This is a perfect setup for the AC voltage divider rule. We know applied voltage, and we know both impedances in a series combination of two elements. An application of the AC voltage divider rule demonstrates V2 to be 74.9 volts at an angle of negative 123.5 degrees, where assumed directional polarity is positive to negative, left to right. An application of Kirchoff's voltage law demonstrates V double prime to be the remaining 45.4 volts at an angle of negative 114.2 degrees, where assumed directional polarity is positive to negative, right to left. Given combined impedance Z double prime is in fact the parallel combination of impedance elements Z1 and Z3, it can be said both V1 and V3 also equal 45.4 volts at an angle of negative 114.2 degrees, where assumed directional polarity positive to negative is right to left. Let's put these values aside and solve for properties for the remaining sources. Similarly, to analyze this system from the perspective of source L1 only, we remove sources L2 and L3 by substituting in short circuits or low impedance paths. This modification has fundamentally changed the nature of our original circuit. It appears as if Z2 is in parallel with Z3, a simplification I'm calling Z single prime. The parallel combination of Z2 and Z3 are two like impedances present as a combined impedance of 182.5 ohms at an angle of 28 degrees. Z1, our odd impedance, and Z single prime appear to be perfectly in series with one another. This is again a perfect setup for the AC voltage divider rule. We know applied voltage, and we know both impedances in a series combination of two elements. An application of voltage divider rule demonstrates V1 to be 90.9 volts at an angle of 5.8 degrees, where assumed directional polarity positive to negative is left to right. An application of Kirchoff's voltage law demonstrates V single prime to be the remaining 31 volts at an angle of negative 17.2 degrees, where assumed directional polarity, positive to negative, is right to left. Given combined impedance Z single prime is in fact the parallel combination of Z2 and Z3, it can be said that both V2 and V3 also equal 31 volts at an angle of negative 17 degrees, where assumed directional polarity, positive to negative, is right to left. Let's put these values aside and solve for properties for the remaining source. Finally, to analyze this system from the perspective of only source L3, we remove sources L1 and L2 by substituting in short circuits or low impedance paths. These modifications have fundamentally changed the nature of our original circuit. It appears as if Z2 is in parallel with Z1, our odd impedance, a simplification I'm calling Z triple prime. The parallel combination of Z1 and Z2 presents a combined impedance of 221.3 ohms at an angle of 37.3 degrees. Z3 and Z triple prime appear to be perfectly in series with one another. This is again a perfect setup for the AC voltage divider rule. We know applied voltage, and we know both impedances in a series combination of two elements. An application of the voltage divider rule demonstrates V3 to be 74.9 volts at an angle of 116.5 degrees, where assumed directional polarity, positive to negative, is left to right. An application of Kirchoff's voltage law demonstrates V triple prime to be the remaining 45.4 volts at an angle of 125.8 degrees, where assumed directional polarity, positive to negative, is right to left. Given combined impedance Z triple prime is in fact the parallel combination of Z1 and Z2, it can be said both V1 and V2 are also equal to 45.4 volts at an angle of 125.8 degrees, where assumed directional polarity, positive to negative, is right to left. Let's put these values aside and summate our previous results. Accounting for not only magnitude and phase shift, but also polarity, it can be demonstrated load impedance Z2 experiences a voltage drop of 100.5 volts at an angle of negative 116.2 degrees, where assumed polarity, positive to negative, is left to right. Similarly, accounting for not only magnitude and phase shift, but also polarity and direction, it can be demonstrated load impedance Z1 experiences a voltage drop of 136.3 volts at an angle of 5.8 degrees, where again assumed polarity, positive to negative, is left to right. Finally, accounting for not only magnitude and phase shift, but also polarity and direction, it can be demonstrated load impedance Z3 experiences a voltage drop of 125.8 volts at an angle of 110.7 degrees, where assumed polarity, positive to negative, is left to right. Given these final summated voltage values, we can solve for current. An application of Ohm's law demonstrates I2 will be 275.4 milliamperes at an angle of negative 144.2 degrees. The phasor diagram illustrates current lags voltage by a relative 28 degrees. Application of the AC power formula using only the relative phase shift demonstrates load impedance Z2 experiences 27.7 volt amperes of apparent power, of which 24.4 watts is directed towards real power and 13 bars is directed towards a reactive interchange. Similarly, an application of Ohm's law demonstrates I1 will be 254.7 milliamperes at an angle of negative 45.2 degrees. A phasor diagram illustrates current lags voltage by a relative 51 degrees. Application of the AC power formula using only relative phase shift demonstrates load impedance Z1 experiences 34.7 volt amperes of apparent power, of which 21.8 watts is directed towards real power and 27 bars is directed towards a reactive interchange. Finally, an application of Ohm's law demonstrates I3 with 344.6 milliamperes at an angle of 82.7 degrees. A phasor diagram illustrates current lags voltage by a relative 28 degrees. An application of the AC power formula using only the relative phase shift demonstrates load impedance Z3 experiences 43.3 volt amperes of apparent power, of which 38.3 watts is directed towards real power and 20.3 bars is directed towards a reactive interchange. Here's our final values. Note for this unbalanced three-wire Y configuration, not only is current different for each branch, so is voltage. Understandably, power consumption for each load differs. Let's now examine total apparent, total real, and total reactive power for this complete circuit. Total real power equals the summation of individual real powers. Substituting our given values yields a total real power figure of 84.6 watts. Note for an unbalanced condition, one cannot simply multiply an individual branch real power figure by 3 because they're no longer identical. Similarly, total reactive power for this system equals the summation of individual reactive powers. Substituting our given values yields a total reactive power figure of 60.3 VARs. Again, note for an unbalanced condition, one cannot simply multiply an individual branch reactive power figure by 3 because they're no longer identical. Given the total real and total reactive power figures, we can now package these as the real and imaginary components of a rectangular number, 84.6 watts plus J 60.3 VARs, and then convert it to polar form as 103.9 volt amperes at an angle of 35.5 degrees, which yields our total apparent power figure. Before we move on, please take a note of these values we obtained for the unbalanced 3-wire Y configuration. We'll do a quick comparison of balanced and unbalanced 4 and 3-wire Y configurations before we close out this lecture. In summary, unbalanced 3-wire Y configurations aren't that hard either because the superposition theorem treats each branch independently and then summates the individual effects, accounting for not only magnitude and phase shift, but also polarity and direction. We rather quickly demonstrated that even this tiger is not too tough to be tied up by the tail and sold to the local dog food factory. As long as you stay organized, the superposition theorem is a great tool for 3-phase AC circuit analysis of unbalanced loads. Before we close out this lecture, let's compare and contrast the performance of balanced and unbalanced 4 and 3-wire Y configurations. Like I said previously, ordinarily an industrial 3-phase AC motor can be modeled as a balanced Y or delta configuration depending upon construction. If a motor exhibits a degree of internal imbalance, its performance may suffer. Consider an ideal 3-phase AC motor modeled as a balanced 4-wire Y configuration, where each branch impedance is modeled as 365 ohms at an angle of 28 degrees. Current through each branch impedance would be 328.8 milliamperes, only I1 has a phase shift of negative 28 degrees, I2 has a phase shift of negative 148 degrees, and I3 has a phase shift of 92 degrees. They're all lagging by a relative 28 degrees. Each branch impedance would experience 39.5 volt amperes of apparent power, 34.8 watts of real power, and 18.5 VARs of reactive power, yielding a total apparent power figure of 118.4 volt amperes, a total real power figure of 104.5 watts, and a total reactive power figure of 55.6 VARs. Given the balanced load currents, no current exists in the neutral line, and if we wanted to, we could remove it without unduly affecting the system. Lacking the 4th wire makes this balanced 4-wire Y configuration a balanced 3-wire Y configuration, and we can retroactively apply the previously obtained 4-wire properties to this 3-wire system. The balanced 3-wire Y configuration in all respects appears as if it were a balanced 4-wire, only we saved money by eliminating the 4th wire. Let's consolidate the stats for the balanced 4 and the balanced 3-wire Y configurations in this table. Really, the only difference between the balanced 4 and balanced 3-wire Y configuration is the presence or absence of a 4th neutral line. Current in the neutral line in the balanced 4-wire Y configuration is 0 amps. There exists no 4th neutral line for a balanced 3-wire Y configuration. Consider, however, our previous unbalanced 4-wire Y configuration, where one of the windings, Z1, has been modeled as an impedance of 535 ohms at an angle of 51 degrees. Our earlier calculations demonstrated load impedance Z1 drew a different amount of current and as such experienced a different amount of apparent, real, and reactive power. Given the unbalanced load currents, an application of Kirchoff's current law demonstrates 155.5 milliamperes of current at an angle of negative 172.4 degrees exists in the neutral line. Note, because of the unbalanced nature of this Y configuration, the motor appears to be consuming less power. As a result, the motor might not be performing its function as capably as previously. The clear warning sign of an imbalanced condition being the degree of imbalance between the individual line currents as well as the presence of current in the neutral line. This being said, applied voltage across the unbalanced elements does appear to be stable. For an unbalanced 3-wire Y configuration, not so much. Again, consider our previous unbalanced 3-wire Y configuration where one of the windings, Z1, has been modeled as having an altered impedance of 535 ohms at an angle of 51 degrees. Our previous calculations demonstrate not only is current different for the altered impedance, it's different in every single branch. To further compound these effects, voltage in each branch is also of a different magnitude. Obviously, given differing voltage values and current values, individual apparent, real, and reactive power will be different. Again, because of the unbalanced nature of this Y configuration, the motor again appears to be consuming less power, only this time more so, principally because the imbalanced current continues to circulate throughout the system affecting the voltage differential across the individual loads. As a result, the motor might suffer an even more notable deficit in performance. The clear warning signs of an imbalance condition here again being the degree of imbalance between the individual line currents and also the mismatch in applied voltage. The point being, you may save money on wire for balanced 3-wire systems, however, they don't function too well in an unbalanced condition. Alright, that's about it for today. In conclusion, this lecture examined the analysis of unbalanced 4 and unbalanced 3-wire Y-configured loads in 3-phase AC systems. We learned that loads in unbalanced 4-wire Y configurations still directly experience the line-to-neutral voltage, and Kirchoff's current law demonstrates that imbalanced current appears in the fourth neutral wire. Really, no special purpose skills are employed in the analysis of unbalanced 4-wire Y-configured loads, and each branch can effectively be treated individually. In contrast, we learned that we needed to apply the superposition theorem, not necessarily a special purpose skill, but a slightly more involved circuit analysis skill for unbalanced 3-wire Y configurations. Loads in unbalanced 3-wire Y configurations may not experience the same voltage because imbalanced current continues to circulate throughout the system. Finally, we learned that total apparent, total real, and total reactive power for balanced, unbalanced 4 or 3-wire Y configurations is still the summation of individual apparent, real, and reactive power figures. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.